So welcome you all to the final session of this foundation module. We have solved a regressor problem followed by a classification problem. And today we are going to see what are all the crucial hyperparameter and different way you can train the model, and also what are all the different options to save the model, and what are all the different way you can monitor the performance metric. See, whenever I use the performance metric, I use the word monitor. So you can monitor the performance based on any metric, but the model will always learn in one strategy. Just because you are monitoring the performance metric in a different strategy, model learning behavior you cannot control. Please be, I have given an analogy. Okay. Just because you have one standard preparation technique, right? But I can evaluate you based on different way I can evaluate you. So this is monitoring is just for our judgment process, but model will have a single goal. That single goal is to reduce the cost function using a gradient descent approach. So whatever the gradient formula we have calculated, whatever the backpropagation learning we have calculated, using that approach, model is going to update the weights. So with the idea of reducing the overall cost function. So the default monitoring, when you run the program, you could see the default is accuracy for the classifier, and for regressor, the default is R square value. But however, we use for regressor mean square error, MSE, or you can also say mean underscore squared underscore error. This is loss function. When you define the loss function for classification model, for binary, we should use binary cross entropy. For multi-class, categorical underscore cross entropy. So here you don't have choice, right? If it is a regressor problem, you have to go with this loss function. So both are same, either this or this. Whenever you deal with the classification binary, it's the loss function. But in a handover calculation, when we define the loss function, I make use of y minus y cap the whole square formula itself. I have extended to solve it, because that will be easier for us to do the handover calculation. But however, when they program this internally inside the API, you may aware of a log loss, isn't it, for classification? So internally, the loss is being written in the form of cross entropy. That is why here we are representing the loss in the form of a categorical cross entropy or binary cross entropy. So the log loss, how do we define the log losses? Y actual log base 2 y cap predicted plus 1 minus y actual log base 2 1 minus y cap pred. So the objective is to minimize this. What is the logic? Let us check the logic behind this. Let us assume I have two y actual, actual labels are 0 and the two labels are 1. But the model has predicted, okay, classification model output in the form of a predicted probability, isn't it? So for 0, model has predicted like this. Perfect value should be 0, but practically it won't exactly predict 0. That we have seen with the example of XOR linearly non-separable problem. We have trained it. Remember, we have got 0.03, 0.036, something, 0.04. That means 3%. This is 4%. Okay, like this. Whereas for label 1, this is something like 0.90. This is 0.95. But strictly speaking, if you look at inside this, it is one hot encoded. It is one hot encoded like this. That is why in sklearn, but sklearn, you don't need to explicitly do the one hot encoding for the labels. sklearn internally, it will show the result in the form of 2 columns. Whenever you do model dot predict underscore proba, okay, for your test record or even training record, if you print, it will show you 2 columns. So the first column is for a label 0. Second column is for the label 1. Okay, so after one hot encoded, how the value you would see, better I try to represent this one hot encoded representation. Without one hot encoding, you will have single node. So single node probability will obtain like this. So let us suppose if you have done one hot encoding, the output node will be like this. So the network is connected like this. Okay, this is the output layer. So all these are the inner layer, hidden layers. So whenever we try to feed label 0 record, we wanted to get the maximum probability for this. Okay, label 0 probability, higher probability. On contrary, label 1 probability should go down. For example, this is 0.85, this is 0.15. Again, the second record also, it belongs to label 0 record. This record has trained like this, maybe 0.90, 0.10. Third record belongs to label 1. Say this is 0.20, this is 0.80. If it is for 2 labels, actually your output side, your sigmoid function is producing this probability. Always the total probability will 1. Whenever you go for multi-class, okay, sigmoid will not maintain this probability 1. We use softmax. So in the yesterday session, I told you how softmax function works. E to the power of the sigmoidal calculation divided by summation of the values. The problem with sigmoid for multi-class is the total probability will not maintain 1. Say for example, if I have label 2 also, for it will produce something like this. Now you can see 0.85, 0.15, 0.25 exceeds 1. So what softmax will do, if this number need to be converted to softmax probabilities, e to the power 0.85 divided by summation of e to the power 0.85, e to the power 0.15 plus e to the power 0.15 plus e to the power 0.15 plus e to the power 0.25. So it is exponentially normalized value. Once it becomes exponentially normalized, this value, now you got new probability, but the proportion it will maintain. For example, out of these 3 probability, we don't waste time in calculating this in the calculator. I just give you a rough figure. Suppose if you apply the formula and you will get the score something like this proportionately, but the total probability it will maintain 1. Something like this. After softmax, like 0.68. This will be the least. Okay, like 0.08, and this will be like 0.18. So this is 2.6. So this should be somewhere around 7.4. Okay, 0.74, 0.08, 0.18. You can see now the total probability to maintain 1. I have given a rough figure, but if you wanted to calculate accurately, what you need to do? Okay, e to the power 0.85 divided by, the denominator is common. What is the common denominator? Summation of e to the power 0.85 plus e to the power 0.15 plus e to the power 0.25. So the numerator only you change. Whenever you calculate for this, e to the power 0.15 divided by this denominator, e to the power 0.25 divided by. So now the total probability your softmax will maintain 1. Okay, this is the structure of your output one-hot encoded representation. Okay, with this representation, I will show you how the loss will be calculated. For our hand work calculation convenience, I have used y minus y cap. Even that method also it will work. Okay, but why it is being represented is because using this loss function, they can also represent maximum likelihood to probability, the concept of maximum log likelihood or maximum likelihood concept. So that is the reason they would like to keep it as a general loss function for the classification problem. So first we'll discuss this quickly. We'll discuss this log loss, and then I'll give you the context of why it is being called as a maximum likelihood log likelihood function. Okay, now we are supposed to apply this formula, right? So how this formula is applied? So now it is calculated as a binary cross entropy. Okay, we can extend this for multi-class. It is the same formula we are going to extend for the multi-class. I will tell you once finishing this, I will tell you how it is extended for multi-class. So this is a summation actually, because you have to sum across all the records. So for here we have only 4 training records as you. So how the computation will go on? Now I calculate for the first record. So here I vary from 1 to 4 records. So negative summation of, okay. So negative here also you will, the whole result you will get negative. That negative into negative will become positive value. So the original formula will look like this. So I substitute y actual like this, minus of, what is y actual? 0. 0 times anything 0, right? So this term will cancel, plus 1 minus y actual. What is 1 minus y actual? 1 minus 0 times log base 2, log base 2, 1 minus of predicted probability for label 0. What is the predicted probability for label 0? The balance. Because the formula is devised based on the single node perspective. See, when you consider in the single node perspective, whenever you present a label 0 record, this guy should reach 0% probability, isn't it? As whenever this guy approaches 0% probability, then this 1 minus of 0, 1 minus of 0, my log will approach to log 1 is 0, we know it very well. Log 1, 0. So in one hot encoded version, 1 minus y cap predict means here to the context of label 0. This y cap predict is to the context of, because you are supplying the label 0 record. So what is y predict? Y predict is 0.85. So y 1 minus y predict is 0.15. I should substitute 0.15. So the idea here is when this y predict try to approach, see for the good learning, assume if the model is perfectly learned, this probability is approaching to 1, right? Okay, label 0 record probability approaches to 1. So when you try to put 1 minus 1, it becomes 0. Similarly, for the second record, 0 times, again the whole term is 0 plus 1 minus 0 times. See, I did a mistake. Let me erase this. See, whenever we substitute the value to the context of binary, your whatever your y cap predict, right? This y cap prediction probability to the context of single node output. All these probability are considered as label 1 probability. So that means I should consider this as my y cap predict to the context of label 1. What is the meaning of, even though we have the balance is 0.85, but how to interpret this 0.15? 0.15, the first record is predicted as label 1 with 0.15 probability. Obviously, we should comprehend the meaning here is only 15% chance for label 1 means obviously 85% chance for the label 0. So the balance probability is obviously the probability of label 0. But you should consider this y cap probability as to the context of positive class. Okay, for the positive class here, since it is 0 and 1 you have encoded binary class. So this is my positive class. And for the fourth record, let us assume this is 0.10, 0.90. Okay. Now let me do the substitution again. So the first two records belongs to 0. Third and fourth record belongs to label 1. So here we write y actual. Y actual is 0, 0, 1, 1. Okay. So minus of, see, whenever I substitute actual label 0, the first term is invalid, right? 0 times of anything. So only the second term is valid. So 1 minus 0 time log base 2, 1 minus 0.15. Okay, earlier I substitute to context of label 0. Okay, the first column is reserved for label 0, not label 1. Okay, I replaced second column value by first column. That was a mistake. So I should substitute the second column value, that is to the context of positive class. So 0.15. So then only if this value approaches to 0, what happened? Actually, meaning is this value approaches to 1. If this value approaches to 1 means this is approaches to 0, right? So your label 0 record, the probability of belong to positive class is only 5% or only 1% means the remaining 99% chance to be label 0. So when this guy approach to 0, naturally you will get 1 minus of negligible value. This is almost close to log 1. We know it very well, log 1 is 0. So your overall this term becomes 0 or very close to 0. How to substitute the second entry? Once again, 1 minus actual label is 0. Log base 2, 1 minus 0.10. 1 minus 0.1 log base 2, 0.9. Again, it's close to 1, right? Here it is log base 2, 0.85. Now, third and fourth entry, look at this third and fourth entry. 1 minus 1 becomes 0. The second term becomes invalid. The first term is valid. So how the substitution will go on? 1 time log base 2. This y predicted probability of positive class. Okay, 0.8. 0.8. Again, 1 time of log base 2, 0.9. So the summation of these 4 terms. So for better trained model, okay, assume that this is somewhere at 1,000 iterations. You increase this to 5,000 iterations. So your model has trained like this 0.95, 0.05, and this is 0.98, 0.02, and this is like 0.02, 0.98. This is like 0.01, 0.99. So comparatively, this loss will be very less when compared to this loss. Now, in the same manner, if you substitute what will happen, log base 2, 1 minus, this time only 5% you subtract. Only 5% if you subtract log base 2, 0.95. Still, it is closer to 1. So this loss will be very small when compared to the earlier. Here 1 minus, only 2% you subtract. That means your log of 0.98, still closer to 1. And this is already very high value, 0.98, 0.9. So this is how we have to interpret the binary cross entropy. So that is why we use the term binary cross entropy in the loss function. Okay, how to interpret the formula for multi-class problem? See, for multi-class, there is nothing like negative and positive. I cannot use the word negative, positive. For binary, I can use the word negative, positive, right? Label 0, negative, label 1, positive. Imagine if you are applying for some bio healthcare problem. Actually, the positive means, okay, disease. Say, for example, COVID positive. Here, the disease we try to represent as a positive. You are doing some credit card fraud transaction prediction. Here, the positive is fraud transaction, fraud. You are building a model for earth sign project, earthquake. The positive label should be earthquake. What is the meaning of positive you should communicate here is whichever is abnormal. Abnormal is what the positive is. We are interested to predict the abnormality. In general, okay, in general, which will dominate? Your negative class will be dominating. See, most of the people are healthy, right? Most of 90% of the people are healthy, or even 95% of the people does not have COVID. Only 5 to 10% of the people have the COVID. Similarly, 98% of the transactions are genuine transactions. Hardly 1% or 2% of the transactions are the fraud transactions. Similarly, most of the days are earthquake-free days, right? Last 2 to 3 years, South India have not, even last 5 years, we have not experienced any earthquake. Maybe tsunami. Tsunami is a very rare event, once in 10 years or something, very rare event. So the abnormality should be coined as a positive. That is why whenever we define the sensitivity of the model, always we try to define the sensitivity of the model with recall score. Recall means sensitivity. How sensitive your model is predicting positive class as a positive class. Suppose truly there are 50 COVID positive cases, okay, and there are some 30 negative cases, and this is how my model predicts. I predict. Okay, this is negative, this is positive. Out of the 50 positive cases, if my model correctly predicts 45 cases and 5 cases it say negative means, how do you define the sensitivity of the model? How good my model is predicting positive class correctly as a positive class. So 45 out of 50, that is the sensitivity of the model. Whereas negative class responsible for specificity of the model. Specificity of the model. Here, say for example, out of 30 healthy people, 28 healthy correctly recognized as a healthy. 2 healthy cases are wrongly declared as a positive. So this is called false positive, wrongly declared as a positive. So in that case, the specificity of the model is 28 upon 30. So specificity is slightly greater than sensitivity here. Okay. Obviously, if you calculate the fraction, you will get slightly higher score for this, slightly lower score for this. So that is why we assign positive to the abnormality class. So according to whichever the domain you work on, you have to figure out which is abnormal. For example, industry fault prediction. You're doing a ANN model for industry fault prediction. So here, whenever the industry, if a particular process going on a fault, that condition of fault should be considered as a positive class. Because most of the time, the plant is operating fault-free operations. Very rarely that fault happens. So your model has to predict. So whenever the parameters, some variable changes in x1, x7, x8, these variables, some value changes, it leads to fault. Okay, so you have other combination of the features for non-fault. So this is about figuring out which category should be referred as negative, which category should be referred as positive. Okay, coming to multi-class. So multi-class we should not refer as negative or positive. Say I have something called healthy, mild diabetic, okay, mild diabetic and severe diabetic. I have three classes. Now, how we define Y actual class? Okay, whenever we feed healthy record, the label should be like 100. This is one hot encoder. Okay, this is for the healthy record. 010 for mild diabetic, 001 for severe diabetic record. Okay, so let me label this guy. This is the actual label for healthy, this is for mild, and this is for severe. Okay, now this is the actual label, but the model has produced different probability, right? Let us say this is Y predict probability. The Y predict probability goes like this. So for healthy, mild, and severe is 75, 0.05, 0.20. Okay, whenever you are training the healthy record, but model learns the healthy record as 75% healthy, 20% chance to be, let me give 25% chance for mild and 5% chance. $75, maybe just 1% chance. Okay, 1% chance for this. This is 24% chance for mild. There is 1% chance. Healthy is obviously whichever the node has the highest probability, model will predict that, because we are going to apply what? We are going to apply argmax to it. When you apply argmax, only this node probability is higher, so it will be predicted as healthy. But our intention is how good we are preparing this probability scores, whether closer to 1. Because as you tune the model closer to 1, your overall log loss will be maintained very less. So the idea here is what? To maintain the good margin between. Still, I don't want to have this 1% score here, right? As if I try to improvise the score, maybe this score will touch 0, and this score will further reduce to like from 24%, it may reduce to like a 5% or 2%. Okay, that is fine. So that is a better training. For the second record is tuned like this. For mild diabetic case, it is something like 0.90. 5% probability there is a chance of healthy, or 5% chance of a severe. Okay, this is the way the second record got trained. Third record, severe diabetic, right? This is like 0.1%, 0.1%, and we'll keep this as 0.80. This is 19%. At this stage, assume I have only 3 training record. For this 3 training record, how categorical cross entropy formula works for this? How categorical loss entropy formula? So same binary cross entropy formula we are extending for categorical cross entropy. Minus of first record. Okay, I'm going to substitute for first record. What is Y actual? Okay, this is Y actual. Here the positive class is with respect to the healthy. Healthy should be considered as the positive class. These two are considered as the negative class. Please understand, for the multi-class. So this is the common formula. Y actual log base 2 Y cap predicted plus 1 minus y actual log base 2 1 minus y cap predict. That means you have to extend this formula. Y actual is 1 and 1 minus y actual. For 2 nodes, you have to extend this substitution. Additionally, you have to extend the substitution for the 2 nodes. So how we can do this? Let me do it here. Y actual log base 2 y cap predict plus 1 minus y actual log base 2. So this is positive class and 1 minus y predict is considered for the negative classes. Here, whenever you consider, even though we don't use the word negative, here in one hot encoding, we call this a hot vector. These two are cold vectors, right? The second term you should use for the cold vector. The first term I should use for the hot vector. That is the meaning. So the extension of this formula to multiple nodes is called as categorical cross entropy. Categorical cross entropy. Okay, let me do the substitution. You can understand how I do the substitution. So minus of, okay, y actual, because this y cap prod is always referring to the positive class, right? So here it is hot node, right? Hot node. What is the probability? 0.75, right? So 1 time log, because the actual is 1 time log base 2, 0.75. Okay. Now you will have 2 substitution. Earlier in the binary, this is, you have only 1 substitution. After positive, you have only 1 negative, right? But here after positive, there are 2 cold nodes. For the 2 cold nodes, how the substitution will go on? 1 minus 0, because the actual label is 0 here. Log base 2, 1 minus this score, 1 minus 0.24 score. For a good model, okay, for the good model, only this node should get highest probability. The other 2 nodes should get the probability close to 0. Assume this value is close to 0, approximately close to 0. This is log of 1 becomes 0, isn't it? So naturally, if the score go down, overall log loss will reduce. Similarly, one more node I need to substitute. 1 minus 0 time log base 2, 1 minus 0.01. So this is almost 1 minus 0.01 is almost like 0.99, very close to 1. So this is very, very small value. So this is, we have done with the first record, right? You have to keep on substituting it. Now you have to substitute for the second record. Second record, how the substitution goes on in the same manner. First for the hot vector, 1. Sorry, here the middle is the hot vector. Okay, this is the hot vector. The other 2 are cold vectors. Okay, first I'll substitute this, the middle one. Okay, 1 time log base 2, 0.9 plus 2 cold vectors. So 1 minus 0 time log base 2, 1 minus 0.05 plus 1 minus 0 time log base 2, 1 minus 0.05. Okay, second record we substituted. Finally, third record. Third record, which is the hot vector. This is the, because in the actual, this is the hot node, right? Hot node. So first, I always substitute the first 2 is the hot node. 1 time log base 2, 0.8 plus these 2 are cold nodes. So 1 minus 0 time of log base 2. For cold nodes, you should substitute 1 minus of the probability plus 1 minus 0 time of log base 2, 1 minus 0.4. See, the same formula, I can extend it for any number of output nodes. So whenever you extend the binary cross entropy formula to multi-nodes, that is called categorical cross entropy. Is it clear? So this is how the binary cross entropy and categorical cross entropy formulas are computed. If you have any question, feel free to ask the computations. Okay, now I'm going to move on to the optimizers. Okay, we are going to explore optimizer. See, in the same notebook, I have updated with today's topic, whatever the topics, the key topics you're going to discuss. We are going to understand the different optimizers. So far, we have used the SGD optimizer only. Other than SGD, we are going to try ADAM, ADAGRAD, RMS Pro. So what is the practical meaning of those optimizers? Why we require those optimizers?
Hello.
Yes, Gayatri.
Sir, sorry to interrupt. I have one doubt.
Yeah,
Uh,
please.
so in a previous thing, like you have told for multi-class, we are using this by categorical cross entropy and the calculation. If suppose if, under that healthy condition itself, we have like some subclasses. So in that case, like how should we proceed and how to approach for that? How to proceed?
Yeah, the original data frame itself, you have to first fix how many classes you are going to work with. See, most of the supervised problem, okay, supervised problem means you have the label known to us. Assume that you are obtaining this data from some clinical lab and the lab is providing you with 1,000 records, and these 1,000 records are already labeled like healthy, mild and severe and all. Let us assume that if it is not labeled, generally what we do, we apply clustering technique. You apply clustering technique. When you do the clustering technique, whatever you have told, that is possible. Say, for example, you see the clusters, 3 clusters you are seeing. Say this is the data point of severe, okay, and these are all the data points for the healthy, and for the mild, let me plot in a different color. By looking at the scatter plot of these 2 classes, okay, health and severe, and when you look at the pink data point, can you notice one variation when you look at the pink data point? Let me remove this dot symbol. So for clarity, what is your observation? Can you tell me there are 2 blue clusters, 1 pink cluster? Can you comment on the pink cluster?
So you are categorizing as highly mild and severity and considering as each cluster.
Yeah, see the what you need to observe, these are all closely placed data point, right? I can say this is highly homogeneous. Yes. Highly homogeneous. This is also tightly packed cluster. Can you see it's a highly homogeneous? They are tightly packed. And this is not a tightly packed, it's a loosely packed. Why I'm saying it is a loosely packed? Because I see a very huge gap here in the middle. That means there is a potential chance, okay, there is a potential chance within this mild category, there are 2 variations in the mild category. So there are 2 subclasses are there. If you do agglomerative clustering, okay, your k-means clustering will not give you the subcluster information. But when you do agglomerative clustering, in the agglomerative clustering, your dendrogram, with the help of dendrogram, you can easily see overall the records are subcluster and these are also another subcluster. Now what you can do, you can take the centroid of this feature. Take the centroid of this feature. Say for example, blood cholesterol level, body mass index, and diabetic pedigree function. So some 3 variable, mean value. Okay. Again, this cluster mean value I take cholesterol, BMI, diabetic pedigree function. These 3 values. Because since we don't have a domain knowledge, okay, we don't have a domain knowledge, I go and meet the diabetologist, or the clinical experts. I just go and see. Overall, this is being coined as a mild. Okay. See, we have got two sub clusters and look at the centroid, these centroids value, but you try to show it in the Z scale. Okay. You are trying to show this in the Z scale. Z scale is a standardized scale. Okay. Say this is 0. Your healthy will be spread somewhere over here, and your mild is spread somewhere here, and severe cases. So with the mild itself, you are noticing two centroids. Okay, this is one portion concentrated, and this is, so you have some gap over here, like this gap you notice. So only the domain expert or the clinical expert has to say that, is there any clinical significance for this centroid and this centroid? If the clinical experts validate or the domain expert validate, yeah, this should be treated as a separate class, means we should give a separate label for it. Or the clinical expert says that no, clinically we'll treat both. There is no special treatment for this case and this case. We give a same therapeutic method for both the cases. So that is why we keep both cases are my same treatment process. So that should come from the domain expertise. So as a data scientist, when I explore the data, all these possibilities are there. If it is unsupervised, there is no label. You are in the process of generating the label, right? When you are in the process of generating the label, who is the end authority to tell that, okay, this is 4 cluster is the final? Even though you do the elbow plot and stuff like that, and you go with some approximate number of clusters, at the end of the day, your client has to validate the number of clusters. You may go and produce 3 results. Sometimes these subclasses may wow the client because there is a new pattern you discovered for the client. Yeah, this is, yeah, wonderful. This is, yeah, true subclass. The same thing you are extending for the cancer data. In cancer, in benign itself, if you go and say that 2 category of benign, that subclass may be interest to the client in that condition. They will say, yeah, we need this as a separate class. Because for this, we need a separate dosage. And for this class, we need a separate dosage for the treatment process. Sometimes these subclasses may be interest to the end user client, or sometimes it may not be interested. Your client may say that, okay, put this together. This is what in practical scenario we use it. So taking the feedback from the client, then you have to label it like label 0. This is label 1. If the client wants these to be a separate cluster, you can keep it as 2 and keep it as label. If the client say no, you can keep the whole thing as a 1 label. So obviously, okay, either original data is already label attached. If it is already label attached, you can go and work with that label. Okay, we are not going to question why it is being labeled like this, and because it has already been labeled by the domain experts. And we go and build the supervised model. If there is no label, you are in the process of discovering the label using the clustering technique. Obviously, you have to interact with the client and come up with number of labels suitable for the data set, and you can proceed accordingly.
Okay,
is that clear?
Yes, sir, it's clear. But if for some case, like for example, we are segregating as we are classifying as dog and cat. In dog, we have some breeds. So which is like it's like a kind of multi-label. Under like dog, we have some kind of subclasses. So in that type of scenario, like how the neural network works in.
See, I understand all your whatever which direction your doubt is there. I am able to figure it out. But you should understand one thing: whenever you make the problem statement, okay, when you make a problem statement, we clearly define the number of classes while define the problem statement. Okay, in your problem statement, your intention, what is your objective? Your objective is to classify dog, cat, cow, goat, sheep, all domestic animal. Your project deals with recognizing, okay, you are recognizing some photograph. Based on the photograph, you need to say figure it out whether it's a dog or a cat or a cow, goat or sheep. If this is your problem statement, you will have 1, 2, 3, 4, 5 labels. Whether it is a German Shepherd or it's a street dog or it's a Dalmatian, your model will say it's a dog because that is how you have labeled it. But on the other hand, if you are developing another project, okay, here, okay, this is a project to classify different types of dog breed. Accordingly, you have to prepare the data set. You take the features of okay, a street dog, and you label this as like a common dog, and the features, different features, and you say it's German Shepherd. This is for the Husky. This is for the Pomeranian. This is for the Dalmatians. You have to collect the training records and you label it. You only label it. I need to have required number of records in my training data, and then you feed the model. Hey, these are all the features of so and so dog. You have to learn it separately. Don't generalize a single dog. Okay, because we only provide the inputs to the model in the form of a features, and we are providing the labels, and the model is going to learn accordingly. It is not like your model is discovering the label for you. Label is already assigned and you train the model. Okay, for the future, once the trained model, okay, somewhere in the future, there is an animal is crossing, there is a dog is crossing a CCTV camera, a camera, the model should be able to say that, okay, this is so and so type of dog, if it is already trained for the variety of dog. But on the other hand, it is just a dog alone, because most of the applications are generalized. Say, for example, for the computer vision applications, the intention is to just to recognize it is a dog or a cat or a sheep. That's all. Whether my application demands a particular dog breed need to be recognized, then obviously I have to add more features to that records, and I have to train it with those label also. See, basically we have to provide the sufficient number of records. If we provide the record, model will learn at the end of the day. So at the end of the day, we have to raise the question, what is my end? What is my goal of my project? We have to define the goal of the project. My goal of the project is to just to classify different animals, or you pick one animal and try to classify multiple breeds, or you are having a very exhaustive project and say that with the dog itself you are going to have say 15 breeds, and the sheep you have 10 different varieties of sheep. Okay, and cow you are going to have another 10. Suppose this is your project, this is how you are formulating the project. Make sure that your training record should have enough number of all 15 breeds. At least in each breed you should have hundreds of records. Now you have 1500 records, different breed of dog, and in each breed of sheep you have hundreds of records, 1000 records on the different breed of sheep, and 10 different breed of cow. See, 100 is a rough number I'm telling, but you should have enough number of all permutations, combination of the features you require, certain number of records. Now you have 2500, 3500 training records. Like how many classes are there? 15, 25, 35 classes you train. With 3000 record, is it correct? To 3500 record with 35 class, definitely your neural network model will learn from this feature. It is able to recognize these 35. Any randomly you provide one pattern of cow, it will exactly is going to say what breed of cow it is, what breed of sheep it is. Provided you should supply the data like this.
Okay.
Are you clear?
Yes, sir. It's clear.
But I'll tell you, but most of the practical problem, the people try to develop model to have generalization. Hope you heard about the term generalization. Generalization is the one term people try to keep it. Say I give you one practical scenario. Say a bank ATM machine, a camera, by mistake, okay, by mistake, no stray dog should enter the ATM machine. Okay, whether it is say they wanted to generalize a dog. ATM machine will not look for whether German Shepherd is entering the ATM room, or a Dalmatian is entering, or Pomeranian is entering. For that application, if any dog other than man, other than human being, your vision system is trained in such a way that whether it is a human being, it could be a man or a woman or a children or a old person or a middle age or a youngster, whatever it is, other than man, if a dog or dog-like animal is entering, it should give alarm. Assume this is an application. For this application, model requires generalization. What is generalization? Generalization means, okay, dog-like features have 4 legs, and this is the average height of the dog from the ground is say 0.75 meters. Okay, the length of the dog is like a 0.4 meters, and it has 4 legs, a short tail. This is a generalization. If there is a dot in the skin, or the hair, the hair of the dog is like this kind of shape, or little bit more fur in the skin, it leads to other variety. So this is like a very specific, whether my application demands, whether the specific detail, if my application demands that, yes, you have to provide all those sample images for the model to learn those specific details, your model will learn. But otherwise, if a generalization is the task, your model will try to generalize dog as a dog, whether irrespective of what. Your weights will be updated only to the generalized features, not to the specific details. But your application demands that you try to keep 3 varieties of dog. Obviously, your weight will adjust in finer details. It will go to the finer details like what is the skin tone, what is the any spots in the skin, or whether it is a short dog or very lengthier dog. It will try to explore that feature in the form of by weight adjustments. So that is the difference between the generalization and the specific. I'll give one analogy to this context so that you can easily relate this concept. See, initially, whenever you build any artificial intelligence model, we try to bring a generalization capability. Then, if required, we can give a specific intelligence. The good analogy is just you consider a 2-year-old kid. Approximately 2.5 years, a kid naturally they try to see different objects in the world and try to ask questions. What is this? Okay, this you teach. This is dog. This is cat. This is car. This is bus. This is lorry. We try to teach different objects to the kids, isn't it? Imagine whatever you are teaching to the kid is general intelligence, not a specific intelligence. The reason is first let the brain tuned for the general pattern. You might have shown a dog picture in the notebook or in the computer screen or mobile screen you have shown. But when you show the real dog in the street, you try to re-emphasize the pattern of the dog. See, this is the dog I have shown in the book. We try to cross-check with the kid whether it's understood the dog correctly or not. But for the very first time itself, you try to teach the kid, okay, for the first time, the kid brain is seeing the dog and you are teaching, hey, look at this 4 legs and look at the tail and all, body, fuzz and all. You know, this is Pomeranian. Another dog you show, this is like a German Shepherd. We have taught 3 type of dog, but you never told it is a general dog. You say it's a Pomeranian, it's a German Shepherd, it is like a Dalmatian. Okay, you have taught it. You are very happy that your kid does. You are taking pride to your neighboring parents. Like, see, my kid by this age itself can able to recognize Pomeranian, German Shepherd, and Dalmatian. Fine, you are overfitted the model, right? You overfitted. And one fine day you take your kid in the evening walk, and the kid watches a street dog. You know what your kid will ask? What is this? Because you have overfitted the model. Because your kid has never saw the features of the street dog. You never taught it. If at all, if I want to make my model, if my model to learn, if I show all the varieties of the dog to the model, if I taught, then only my brain will try to say, what is that? It will not possess a general intelligence. Rather, if I taught the general intelligence to the model, any type of dog, Even that variety of the dog you never taught to the kid. But what your kid will say, one dog it will notice in the park, it may be a different variety. Mama, Papa, see, this is a dog. That is a general intelligence. So whether the specific classification is needed for the project is or needed or not, yes, their specific need may rise. But accordingly, you have to make sure that whether I have enough number of sample to show to the model, present to the model, to train to the model, that you have to keep it in mind. Model itself automatically will not evolve and say that, hey, you have taught me only general intelligence, but I am telling you this is Pomeranian or German Shepherd. Only I have to teach the model. To teach the model, I need samples, either in the form of a picture or in the form of a extracted features. So these are the general points that you should be aware of. Not only neural networks, this is applicable to any machine learning models. Hope you got much clarity on this.
Yes, sir. It's very clear now.
Yeah.
Thank you, sir.